Hey Kevin, is this making a sound? Okay.
All right. Hello, everyone. Welcome to Lecture 3 of Gridspace's 2025 IAP series. So this is our Building Sound series. We're doing music and sound synthesis over the course of the next few weeks. Just a reminder of what it's looked like so far. Thanks for bearing with the delay to today's schedule because of current affairs. So last week we went through engineering a song from scratch, and then we saw Natalie give a lecture on DSP, acoustics and signals. Today we're going to be diving more into like the synthesis of sounds, so starting with one of the most intuitive ones, additive synthesis, and then we've got noise engineering here to show some of their modular synthesis, and yeah, give us a synth show. Next week we're going to look at subtractive synthesis, some other types such as wavetable, granular formants, sampling. The week after that, we're going to start diving into our speech synthesis series. So we're going to look at concatenative and parametric TTS and some of the history there and early models. And then we're going to get into kind of modern neural TTS. So that is kind of what the next few weeks look like. Thanks for tuning into Lecture 3. And we're going to start on additive synthesis. Is there any other course admin to go through before we get started, or?
Go for it.
We're good? All right, great. So I called this the most intuitive form of synthesis. We've kind of seen in DSP like the acoustics of like signals and generating sine waves. And so if you were to look at an instrument like a tuning fork, which theoretically has a perfect, in an ideal world, a perfect single fundamental frequency, then that might be enough. But as we all kind of, I hope, know that instruments don't have perfect singular fundamental frequencies, and it's an additive mix of a lot of different frequencies that give us the timbre that we're used to seeing in different instruments. And so that's why a piano might sound completely different from a saxophone. And it's the ratio of these different partials, we're going to call them, that create the different sounds of the timbres. And there's two types of partials which are kind of pretty clear here. There's the harmonic partials, all of which are integer multiples of the fundamental frequency. The fundamental frequency being the pitch that we hear in the note. And then there's inharmonics, which is everything that isn't an integer multiple of the harmonic. And so just again, to overview the types of synthesis, we've got additive, subtractive, wavetable, modular synthesis, frequency modulation, and physical modeling. So we're looking at additive today. And within that, we're going to look at harmonics, inharmonics, timbre, some of the history, some of the modern synthesis, and then I'm going to hand off to noise engineering. So that's the way today is looking. So just to quickly go through harmonics. So Natalie showed us a bit of this, but essentially when you're creating any sound from an instrument, what you're hearing is the standing waves set up by whatever the oscillator in the instrument is. So be that a string in a guitar or kind of pressure waves in like a saxophone or some kind of wind instrument. And the standing waves take kind of the first harmonic, the second might be something like this. This is for a string. And we denote it with a node being anywhere in the standing wave that it is always zero, the amplitude is always zero, and the antinode being the place of maximum oscillation. And so different types of instruments have different setups for their standing waves. So you can think of it as like a string has a forced node at either end. Either ends of the string is forced to be zero always, that's not going to oscillate. Something like a flute, where it's an open column of air that's open at both ends and you blow into it, you're actually forcing an antinode at each end. So yeah, so for the string, that's kind of what we've seen so far. Forcing an antinode at each end means that the standing wave is kind of a quarter of the wavelength phase shifted from that of a string, but the same integer multiples exist, right? As in this top one here, the fundamental on a string is still half a wavelength, which is true of here. Here is still one wavelength and then one wavelength still with two antinodes. And then something more like a clarinet or reed instrument, where it's closed at one end, but open at the other end. So the reed is closed, the other end of the clarinet is open. We actually have a forced node at one side and a forced antinode at the other side. So this gives us something more like this. And in this, the actual kind of frequencies produced, the harmonic frequencies are different. So our fundamental is actually a quarter of the wavelength of the pipe. Our first overtone, our first harmonic, is then 1.5 of the, sorry, no, 3/4 of the wavelength of the pipe, etc., etc. And so this gives us a different harmonic spectrum for different kind of styles of instruments. So a flute, as you can see here, has twice the number because it has all of the odds and the even frequencies, whereas anything in a closed pipe actually skips the even harmonics. So here we only have the fundamental, we have the 3/4, we have the next. Any questions on that so far? Cool. So yeah, and then we add these harmonic frequencies up and we get our timbre and we're done, right? That would give us sounds where everything's vaguely the same. So that's an example of open pipe. So that's just the fundamental frequency, 2 times the fundamental, 3 times the fundamental. And then this is open where we're skipping the evens. So obviously not every closed pipe sounds like every other closed pipe, and not every open pipe sounds like every other open pipe, else there would be no need for multiple types of closed pipe instruments, right? And, oh yeah, sorry. So this is just kind of the additive summation of integer multiples of the fundamental frequency for harmonic frequencies. So in harmonics are then what make each of the two things is what makes each of the instruments sound different. One is the ratio of the partials, so the ratio of the harmonics. To kind of look again here, you can see that this actually, the amounts of each of one is going to make a different, contribute to a different sound. And the other is the inharmonics in the timbre. Yes?
Is a person an open pipe or closed pipe? The tracheolarynx system. Repeat the question.
Oh, sure. The question is a human an open pipe or a closed pipe? And the answer is, I don't know. I don't think I don't, ask Google and get back to me. Ask ChatGPT. Yeah. So this is the form then for inharmonic partials. So as you can see here, instead of having an integer multiple of the fundamental, this can just take any value. So this is any frequency that isn't an integer multiple of the fundamental frequency is classed as an inharmonic partial. And these are caused by anything that might make the standing wave less than like completely idealistic. And we all live in the real world. We know that doesn't really work. So that can be intrinsic characteristics of the instrument itself. So like an example being a guitar string is not going to be, at the points where the string is attached to the instrument, the string has like bending characteristics. It could be the shape of the windpipe. It can be things specific to that individual instrument. So like the exact type of string on the guitar, or it might be even wear and tear cause different properties of the string bending and that kind of thing. Woodwind, kind of your mouth position is a big factor in that. And so that brings us to timbre. And like I say, the other thing is the ratios here. And actually the ratios also depend a lot on like the initial character, like how hard you pluck the string, where you pluck the string, that kind of thing. So moving then into like how you actually synthesize a sound once you've analyzed it. Essentially additive synthesis is literally just adding up all these frequencies and you get a sound. Sounds easy. It sounds intuitive at least, but in reality it's like any of these things where there's so many different possibilities. Being able to analyze a sound such that you can perfectly reproduce it is difficult. Having enough frequency oscillators to be able to perfectly reproduce something natural sounding is also extremely difficult. And so just to kind of go through a brief history of why these have been kind of hard to produce and why they're not more common. So, I mean, starting off with something like Fourier, when Fourier's kind of first published all of his stuff, one of the first kind of sinusoidal synthesis machines was actually a tide predictor. And they kind of analyzed the Fourier coefficients of the tides. And they built this machine to actually synthesize what it's going to look like in the future as a tide predictor. The first kind of way this translated into sound was Hermann von Helmholtz and Rudolf Koenig. And they built an additive synth out of kind of electrically excited tuning forks, which is pretty cool. And then some kind of resonance chamber. The telharmonium is the kind of famous first additive synth instrument. It's the first electromechanical instrument. And this was with AC currents, essentially. So kind of different brushes on a voltage generator causing different frequencies in the current. But they didn't have any kind of amplifier, so it's huge because they needed a voltage generator that could generate enough amplitude to be able to make a sound. And that brought us to the Hammond organ, which was essentially the same principle, but they had an amplifier. So they made it smaller. And so just to play this is 1935. Some bits of it. Yes.
I think it's worth noting that particular Hammond sound sounds like it's less like rotating speaker. That's an important part of the puzzle. You know, the way it sounds real oscillating.
Say that one more time.
You know,
I
that
can't hear.
sounds real oscillating kind of the tone,
Yes.
because they're typically paired with the speaker that had like a rotating horn. It's constantly pointed towards you and away from you.
Just to repeat that, that kind of oscillatory sound that we were hearing in the synthesis is actually the amplifier having a rotating speaker. Am I saying that right?
Yep.
Cool. Great. So then fast forward to digital era, and 1979 was the first commercial digital synth, additive synth. This was the Synclavier 2. The first commercial one. There were ones earlier than this, but... And we can kind of hear how much that's improved. And digital allowed you more flexibility with the amount of, like, your size. You could have more harmonics without it being too large. And then 1996, another famous one was the Koi K5000. So the kind of key takeaway here is how much all of these efforts were trying to reproduce instrumental sounds and struggling, because producing a natural sound with all of the inharmonics that go along with that takes a lot of different sinusoids, and it takes a lot of very careful analysis. And so additive synthesis kind of went out of mode because it was creating less rich sounds than something like subtractive synthesis, which you'll see later. It's kind of had a recent resurgence because digital era and computer era, it's a lot easier now to actually analyze this, and it's also turned into more of like, you can make your own sounds. You don't have to be trying to reproduce a different instrument. You're literally just, you have full control over what frequencies you're adding together to make kind of whatever sound you want. So yeah, that's kind of the modern era of additive synthesis. An example being Loom 2, 2017, and an example being, I believe, Noise Engineering 2024. A new one? Okay, cool. To re-say that a bunch. So any questions on that kind of very brief overview of history of additive synth and just like how, like the underlying principles of additive synthesis before I hand off to Noise Engineering? No one's got any questions. Cool. In which case, I'm going to hand off to Anthony, who's going to introduce our special guests.
Well,
Yet again, Natalie, unfortunately, cannot be here, so I'm just kind of filling in for her. But as Phoebe kind of hinted, oh, actually, I had a question for you, but anyway, I'll ask it. So obviously, we're going to be working our way up from these very kind of simple synthesis techniques all the way up through different methods of synthesizing like speech. So like if you have something like hi-fi GAN as a vocoder for speech synthesis, you're actually inverting a full spectrogram instead of just a list of harmonics. And so obviously we're really excited to show like this long history of different ways of making sound, because all of them obviously have been coming together. Obviously the next week or so, we're going to be talking about other synthesis techniques. So Nico's going to be talking about subtractive synthesis. Uchi's going to be talking about FM synthesis. We also have John Chowning, the inventor of FM synthesis, joining us for that. And then we're going to be also talking about sampling and formants and stuff. But we thought the best way to set all of this up is, so we have noise engineering here. Chris and Steven, thankfully, were able to be here. Nico and I have known you guys for how long, like 5 years, 6 years? Yeah. They're also an LA-based tech company that is excited and very nerdy about sound and audio. Probably the only ones that have us beat in that regard. And Steven is the only one I know who has more sound and audio textbooks than me. Which gives them infinite credibility. But they're going to be kind of doing an overview of modular synthesis in general, which is going to set up kind of the rest of the series to show all the different techniques demonstrated on their hardware. Definitely check their stuff out. It's amazing. So anyway, thank you very much. Welcome Noise Engineering, everybody.
I have to read. Nope. Things moving around. Okay, thank you for your patience there. We are Noise Engineering. This is, well, first we'll start off with just doing some intros. We'll talk a bit about modular synths and history, what they are, how they work. And then we'll talk about a few DSP case studies of some of the products that we have in this case, and just our products in general. So at the end of the lesson, you should be able to describe modular synthesizers and how they differ from fixed architecture synthesizers, and we'll talk about that, and describe some of the DSP techniques that we use, which are not unique entirely to noise engineering by any stretch. So who we are. This is Steven. I'm Chris. We are 50%. We're the owners and founders of Noise Engineering. We are 50% of the company, so half of us are here with you today. We have released over 70 different modules, 11 plugins, and soon to be 2 guitar pedals. So we've learned a few things over the past few years. And so I'll definitely say stop us at any time with questions. We are happy to answer anything. There's no dumb question. If you don't know, somebody else probably doesn't know. So please ask anything that you want, except Anthony. Okay, so modular synths are really flexible instruments. So they can be used for sound design, just getting ideas, effects processing, loops and samples, full compositions. A lot of our customers just like to use them for noodling. They'll want to walk away from the computer and just put their hands on something to make sound. And it's a really big source of noodling and inspiration for a lot of our customers, basically just because it is extremely tactile, as you'll see. It was pioneered, modular synthesis was pioneered by Bob Moog, which is this guy over here, and Don Buchla over here in the 60s and 70s. It was a very different format then, but on the bottom of the screen, you can see a couple or three of the sort of stereotypical and very famous synths, modular synths from that era. In the 90s, a format called Eurorack grew out of this Doepfer A100 series. So 95, Doepfer released this all analog system. Analog Systems, a different brand, released an analog system in 98. But by 2013, there were over 80 manufacturers. Sorry, by 2013. By 2018, there were over 300 manufacturers on Modular Grid, which is just a website that lists every module ever made. It's pretty handy. And now there's easily 1,000. And a really cool thing about this is that every one of those manufacturers, if you buy a module from 5 different people, you can use them together. They play really well together. So modular synthesis is about building a system out of whatever products you like. You don't have to stick to one brand. You don't have to be brand loyal. So why modular synthesis? Fixed architecture synths are awesome. They're great. But sometimes you want to be able to change the signal flow yourself and have a different signal flow. So modular synths, I like to explain them as just exploded fixed architecture synths. So a fixed architecture synth is pre-wired. It comes with, if you buy one of these synths, all of the soldering is done under the hood. All of the connections are made that could be made. The features are generally pretty much set on it. Most of them will have lots and lots of presets. You have no control over the signal flow. There's generally a keyboard, because it's a keyboard. So if you want to play an A, you hit the A key. It's pretty straightforward. You just press a key, you get a note. They're very repeatable, and the clock is usually implicit. Modular synths are very different. You have to make all of the connections with a patch cable. So you're routing the voltage. There's nothing connected under the hood. And I have a couple of modules here to pass around so you can see what I mean. There are things, of course, soldered to make them into modules, but if you want to actually connect this module to another thing, you use a patch cable, and that's how you send voltage around. So I'm gonna pass this around. As a result, so you're making all the connections. You can swap out any module at any time, which means these things are infinitely customizable. Every time you patch, you have a completely new instrument. There are pros and cons of that. So there are no presets in modular, which means that you really, really can struggle to recall a patch. If you really like something that you have, record it, because you may not ever get it again. But you do have complete control over the signal flow with a modular synth. These generally do not have a keyboard, so we'll be patching up here. There's no keyboard up here. The video that we were playing when everybody here walked in, that was somebody playing. He did have a keyboard attached to the modular synth, but that's not always the case. So there's no keys. There's no A key to hit to get an A. So you have to tune it by hand. So if you have an oscillator, you have to tune that to whatever you want it to be. Unlike a piano, so when you have a piano, you hit a key, it makes a sound, you remove your finger, eventually the sound stops. In modular, the oscillator is always putting out sound. So you have to invert your thinking to think about how you want to shape your sound to turn on and off. And then there's no internal notion of clock, because again, each one of these, as you see, we're passing these around, but as you'll see, each of these is a completely separate product. So it can't possibly know what the clock is from a different product. So you have to send a clock to whatever needs to know about the timing. And we're going to do some patching to make some of these concepts a little bit more obvious. Modules are typically characterized by function. So there are oscillators, your sound generators. There are things that they're sequencers and rhythm generators that just help you sequence either pitches, modulation, rhythm, whatever. There are voltage-controlled amplifiers, or VCAs, that help you shape the amplitude. So that's how you turn a note on and off with your oscillator. There are envelopes that help shape the the VCA control, and just do modulation in general. There are filters for your subtractive synthesis that you'll learn about next week. Low frequency oscillators, LFOs, again, really great for modulation. Gates and triggers, those are the things that tell things to turn on and off. There's clock modules, effects, there's so much more. There are so many manufacturers in Eurorack that basically, if you can dream it, somebody probably has made it. Or the barrier to entry is pretty low and you could. It's a very straightforward format, but it's also, because the barrier to entry is pretty low, there are just so many ideas. And it's a really fun type of synthesis. And just to kind of connect to something that Phoebe said, so modular synth, we're going to show an additive synth today, an additive module, but you can do almost any kind of synthesis with modular synths, which is really cool. So if you buy a fixed architecture synth, it's going to be pretty much set to what it can do. You can set this up to be additive, you can do subtractive, you can do granular, you can do pretty much any kind of synthesis with modular. So this is our setup. We have a small case up here. We have a clock module. So small clock module. This is, again, everything. If you're having a clock in your case, if you want anything to be synced, you have to send that clock around. So this is our clock. This is our sequencer. This is what's going to sequence it's going to modulate all of our pitches and rhythms. This is another rhythm generator. So we have two different types of sequencer in here. Both of those will need a clock because you probably want your clock or your rhythm and your pitch modulation to have some sort of internal notion of what the timing is. I'm going to skip this one for a minute. We have an oscillator. So that's our sound source. And then our envelope and VCA. So this is how we turn it on and off. We have a filter, and it's a formant filter, so we'll talk about that. And then we have a complete voice here, which is an oscillator that has this shaping stuff built in. So it's a little bit less complicated to patch because you have to tell it when to go, but it's a pretty straightforward. You don't have like 3 different modules. Yes, question.
For the clock, is there like a limited number of modules that you could set the clock because of the phase, or is there like a module that you can like extend connections?
You can, they're kind of, a kind of module that was not mentioned is called a mult. And that that's actually, there's actually one built into this case, but you can split signals.
The question was whether there's a limitation to how many clocks you can send out.
Well, just the clocking can get very complicated in module because you can have modules that delay clocks, and so you can actually get all sorts of crazy complicated time skew too. So that sort of the clock tree in modular is sometimes problematic. Yeah.
All right, so let's do a little bit of patching. And Kevin, if we could get the camera for the case.
Okay, we should have sound as well.
So all of the, well, okay. So right now we are hearing our additive oscillator, Toro, Ceteritas Alia. We just call them, all of our products have these very weird Latinish names. Just call it TIA, much easier. So this is the TIA. This is an additive oscillator. We're going to talk more about the DSP in this later on. So right now,
it's PM, phase modulation and additive.
Yeah. Right now, all that we're hearing is one oscillator. It's going to the mixer and then going to our output module. So there's nothing fancy going on here. But what if we want to shape it? We want to start using the envelope to, we want to start using the envelope to, and VCA to turn the note on and off. So my illustrious assistant here will be helping with patching.
Is this one? Look in the VCA.
Nope.
That's the other one. Oh, this has bleed. slower.
So now with just 3 modules, you have the oscillator going, you have a voltage controlled amplifier that turns sound on and off, opens and closes as the voltage that goes into it goes high. So this is just a really simple ADSR attack decay sustained release envelope going into the VCA. Okay, so now let's check out the filter. So get rid of the entire the shaping part, the envelope and the VCA, and we're just going to go straight into a filter. And this is sort of a prelude to your subtractive synthesis lecture.
Oh. Yeah, wrong cable. It happens a lot, but it sounded pretty cool, so.
So this is the TIA oscillator going into our Falaversia, which is a formant-ish filter. And that's all that you're hearing here. There's nothing else happening. Add a pattern. So now we can add a pattern, and so this is kind of color-coded up here. The orange ones are your clock, the orange wires on a clock. The cyan is modulation, and then red is your audio path.
Not color coding.
No.
It's too complicated. I am going to swap this to here. So we're going to get a cooler rhythm.
That is not the same patch. That's fine.
Yeah.
So he is building a slightly different patch than what I have on the screen. Marital bliss.
That's where it goes.
So now we just have a couple more modules added in, but these are sending voltage across these wires to help to tell the module what it should do next. So sequencing a pitch, sequencing the rhythm, sequencing what's called control voltage. So basically turning the knobs for us without our hands. Any questions so far? Yes. So the question is whether the melody is stored anywhere, and it's not. Right now we're using a generative sequencer. So if I turn this down, then it'll store that sequence, and it'll keep however many. Yeah, so it'll loop for until I change it again. But right now, when we turn it up to infinite, it just continually generates something totally new.
But it's parameterized, so you have a lot of sort of general controls over it, like the sort of direction that it moves, and then sort of how far it moves, and then also the subset of the scale, I guess. So we can make it like minor very easily, for example.
Okay, so Stephen has basically jumped the gun and done this quick patch.
Yeah.
Do you want to add in Tim?
Yep.
So now we're going to add in our complete voice, which is our Tim Legio module. The names don't matter, but this is a complete voice, so it's meant to be kind of like a favorite drum. Oh, hi.
Hi. Yeah. Yep. Let me slow all this down a little bit.
All right. So any other questions before we kind of move on? We're going to move on to some other specific products. And if there are anybody that's here can come up and play and patch. I definitely encourage people to plug things in. You will not break it. If you do, we know how to fix it. But you will not break it just by plugging things in. So come up and patch and have fun when we're done. The worst thing that'll happen is that you get a sound that you don't like, common, or you won't get any sound at all, which is even more common, until you figure out what things are supposed to go where. So please come up at the end and patch if you want to play. Okay, so we're going to focus on a few of our specific products. One is Dystopia, our first guitar pedal that came out in the fall. It's a digital futuristic fuzz pedal. Then we'll talk about Falaversio, which is the formant-ish filter that we were playing with here. It's based on speech concepts, but you'll hear it's made to be much more musical and not so much focused on technical formant information. And then finally, we'll talk about the TIA, which is the oscillator that we were playing with up here. It's a multi-operator phase modulation drone oscillator, additive. It does a lot of things. So from here, I'm going to turn it over to Stephen to talk about some of the DSP stuff. And I will start with just a quick video showing dystropia in action.
Okay.
Did Emily Hopkins use dystropia too?
Yes, she did a video for us. Yeah, indeed. Yeah, she's awesome. Next slide. Oh, there we go. Okay, so we're gonna get a little more technical. We're gonna talk about some DSP. We're going a little bit of code, not much code, but a lot of signal diagrams. So on the right here is a signal flow diagram for the pedal you just heard. It's a pretty complicated collection of distortions and granular processing and all sorts of weird nonlinear stuff, really. We do all of our development in C++. That is what is on the left there. We do sort of, well, rather functional style C++. So the bottom left of that is the signal flow diagram, basically, but it is, as you can see, like very, very simple and clean. We use functors a lot to essentially just hide state from the actual signal flow, because inevitably when you're working on building these signal flows are they're complicated, they're hard to read, they're hard to debug, and so this is one of the ways, just coding techniques we use to make that better. So a lot of functional style DSP, pretty much everything, like all of our reusable blocks are built with functors with sort of just additional methods for things like inserting the position of the knob into the DSP comes through a different method. The great advantage to this is just the code is the easiest I've seen. I've seen a lot of code where sort of state is intermingled with the signal flow, and it just makes it very verbose and very hard to manage. Okay, so Falaversio. So this is a formant-ish filter. So let's first of all define a formant. So your throat is a big filter. Most humans will produce essentially 3 peaks in their, if you look at a spectrogram of their speech. Particularly the bottom 2 are very critical in understanding of speech. They determine the phonemes you hear largely. They're one of the most important perceptual cues. Yeah. It depends on if your mouth is open. I mean, does that, I guess? I don't know. The pitch doesn't seem different, but then the filtering effects of it just being closed are sort of hard to remove from it. Sorry. Yeah.
What's the main oscillator? If the larynx is the filter?
Your vocal cords. Yeah. The question that was just asked is, what is the oscillator in your throat that is being filtered? And it's your vocal cords. Which are neat. I've actually recently had them stick a camera down and got to see my vocal cords with the strobe. It was kind of cool. The two bottom peaks there are the most important for speech. Most people have 3. Interestingly, some singers actually produce 4. Particularly that's common in really good tenors. So Pavarotti has more formants than you do. So we take that sort of formula, 3 formants, break it down. We build it a similar structure, 3 bandpass filters. Those are individually run through saturators because nonlinearities are awesome, I guess. Then on the diagram there, the little switch just indicates you can, on the front panel, you can control which of the 3 formats you want to use. Very straightforward. We then take 4 of those sets of 3 filters and put them in parallel, and then those are driven by low frequency oscillators so that they kind of spread out in frequency to give it a lot of texture. So that's obviously not something that is going to go on one person's throat. However, it's not too different than having sort of multiple singers. It sounds cool is the bottom line there. The rest of this effect is just some volume compensation and a limiter, which are both, when you're adding a bunch of parallel resonant things together, levels can get out of control very quickly. So there's a whole bunch of work to just keep it in line, basically. And then there's some more distortion at the end. So Fala also has we haven't talked about the input. So before all of those filters, we do a little bit of input processing. So there's a noise gate just to keep the noise. It'll just, if there's input is quiet, it makes it quieter. So you don't pick up noise in the filter. Particularly with resonance, you can get some pretty gnarly noise amplification. We run it through 3 all-pass filters. So this is in like kind of, well, in normal subtractive synthesis, waveforms like sawtooths are very common. Sawtooths perform very poorly with a lot of nonlinear effects, because like if you try to saturate a sawtooth, you get a sawtooth, so it doesn't actually do anything. So the goal of those all-pass filters is actually just to kind of distort the shape of it without changing the spectral content. So that'll actually take a square wave and make it into a much slopier looking thing, but it'll sound the same. So then we soft clip that. That's actually just to prevent clipping from the all-pass filters, because they will often produce transients that are outside of the sort of normal or the input amplitude. And then we use what's called a wave folder. A wave folder sets a threshold and basically just folds the waveform over so it reflects it in amplitude. This is a very aggressive sound. They're pretty common in modular. And they also perform poorly on square waves, hence all the all-pass filters. Okay. So yeah.
What is an all-pass filter?
An all-pass filter is a filter that does not change the amplitude of any frequency.
So you say 100 hertz.
That is the point of 180 degrees phase shift. Yeah. So obviously a circuit that doesn't modify the signal as an all-pass filter, but then a circuit that only affects phase is also an all-pass filter, which is usually the interesting thing. So those frequencies listed are where the 180 degree phase shift point is, and it essentially will from 0 to max frequency, flip it all the way around. Phase-wise, it'll do a full 2 pi across the range, and then you can kind of place where you want the halfway point. So those are all biquads. It's which is a kind of filter implementation. So that's a pretty normal, simple filter to use. Yep. So Toros. So this is a there's 3 algorithms. This is a kind of term from FM synthesis, which is sort of like Chris was saying, how fixed architecture synths, you can't kind of replug them. FM synths have kind of a limited way of do that usually, and they call those algorithms, and I'll show you diagrams of those. The kind of what is interesting about this is that it does some signal flow changes that actually make it a lot more performable as a synth. Let's go to the diagram. So, the top signal flow diagram there's 4 oscillators. It's very symmetric. There's essentially 3 oscillators in parallel, and the blend X controls between blending between modulating the 4th oscillator and then just being mixed into the output. I'm tempted to just do an example here. Let's do this. Yeah, I just want to go straight. Don't want any of that. Nope. Okay. Oop. Okay, let's zero it out. So all 3 of these are just making a pure tone. I can offset the pitch. And so this is just this is with the blend X knobs all the way down. So it is just additive. You'll hear three pitches together. There's a bit of a non-linearity at the end, so you do get some mixed products from that. Let me just zero this out again. But then I can also, the blend X knob, so that's a kind of very typical FM sound, but that allows me to blend from essentially additive synth to FM synth in one control. And you can, you know, just put little offsets and produce all these crazy textures. So that is the first mode. The first algorithm. There are 2 others that are more extreme. I can just give you a quick characterization. So they essentially changed the way, rather than being parallel structures, there's series modulation structures. The modulations get a lot wild. So it's the middle mode, and it's basically just 3 in a row. And the third mode is 3 in a row, except where the output feeds back into the first mode, so you actually get feedback, which gives you chaos. You get also really crazy noise. Badly behaved sounds. Okay. So there's the 3 products we're gonna was that a question? Oh no. Okay. So the last section, we're going to talk about one of the techniques we use in almost all of our oscillators. It's kind of weird, honestly. Phoebe actually introduced a lot of these terms already that I needed to introduce, so I will go through them very quickly. So if you have a sound, the fundamental frequency is generally the lowest, sinusoidal component of that sound. Musical sounds are generally harmonic. So that means that the main power is spaced at integral multiples of the fundamental. Musical sound, so particularly in Western music, pretty much every interesting like melodic instrument has a harmonic partial structure. So, interestingly, there's in the gamelons actually have really non-harmonic but still musical structures, a whole exception. But for the sake of this conversation, we're going to assume that musical sound and harmonic sound are essentially synonymous. So the Nyquist frequency, we have to get into a little bit of sampling to talk about this, is just half the sample rate. That's the kind of important part for what I'm going to talk about. And so then aliasing, and I'm going to kind of overly simplify aliasing and define it as a frequency component that when you sample it, ends up in the wrong place after you've done your sampling. So that could be, typically it's out of bound, or like if it's above the Nyquist sample rate, it'll get frequency shifted if it's not filtered out and end up in the wrong place. Okay, so why is this an interesting technique? So first off, it's not a new technique. Some early samplers used this technique back when they actually were playing one sound back on one DAC and controlling the pitch shifting by controlling the frequency of the DAC. That's kind of this technique is just sort of naturally comes out of that. Um, and so and one other point here, by variable sample rate, we're specifically going to choose a sample rate based off the pitch of the sound. That's not quite specified on the slide. And if you think about sort of making a naive square wave, right? So you're just going up and down, waiting a while, coming straight down, just like you would, perfectly straight. Don't worry about aliasing or anything. If you try to map that square wave onto your sample grid, unless, well, very rarely will they ever align, essentially, because your pitch is going to be sort of continuously variable on that grid. And so only if that period actually divides your sample rate will actually perfectly line up on the grid. So like that is once sort of an intuitive way to think about aliasing production in the time domain. Is just that your square wave doesn't align on the grid. If you think of it in the frequency domain, and this is a little, it's not actually hard to prove, but I'm not going to go through the math here. If you have a harmonic sound, and the fundamental divides the sample rate, then the aliased frequencies are actually also harmonic, which is a really interesting property. They actually will, when they alias, they'll fold back over and align on top of the harmonics of the sound. We'll have pictures of that in a second. And the bottom line is this: it sounds cool. It's a different, like, anti-aliasing is obviously a big problem in a lot of DSP. And this is a way to sort of just get around it, to sort of make it sound better and sort of embrace it. We have a simple graph. On the left is a frequency plot. The yellow lines are amplitudes at different frequencies. The right is just the sum of all of those parts. So this is an additive synth, quite simply. You can see the sawtooth is the Gibbs squiggles, but it's definitely doing a pretty good job of approximating a sawtooth wave. So if we band limit this and sample it, then the alias harmonics. So it's a little tricky to see, but if you start kind of at the highest amplitude and follow it down, that's the same as the curve of amplitude. So when you hit the Nyquist frequency, the aliases actually reflect back down, and then when you hit the bottom again, they reflect back up. The graph on the right, this is not a very good sawtooth. That's the thing to take away here. And you'll notice, well, and this is, the pitch does not divide the sample rate on this. So in the next one, we select the pitch to divide the sample rate. We have a much better sawtooth. It's not as good as the first one, but then the bandwidth is also a third. So like it's pretty good for how little bandwidth we're using here. But if you'll notice, like all of those harmonics align to the pitch. So this previous one, there's a whole lot of inharmonic noise, right? All those harmonics will not meld with that fundamental pitch or the fundamental frequency to give a pitch. However, with this one, all of the aliasing, which would have been noise, an inharmonic noise, basically, aligns, and it sounds great. It doesn't give you the exact waveform, but it still keeps it very musical. Okay, so these are the three time domain graphs. So the band, the full, the non-band limited version, the inharmonic version, and then the harmonic alias version. And we have a video, hopefully that's coming through. So the top is the harmonic and the bottom is the inharmonic. You can see in the time domain on the bottom one is just all over the place. The temperature is going to be totally different for different pitches. It's going to be inharmonic, essentially all of the time. There's going to be a lot of inharmonic components to it. But then the top one, you can see like the waveform stays very stable across the different pitches. Yeah.
So the difference here is just that the Nyquist frequency is set such that the harmonics are aliased, not the
Yep. Yeah, the top graph are actually changing the sample rate. So if you look at the x-axis, the top graph, it's a little hard to see there, but if the x-axis is actually changing along with the right, and then the bottom we're changing the pitch, but the sample rate stays the same. So yeah. So yeah, we're in the top graph. We're actually always picking the Nyquist frequency is 5 times the pitch, just arbitrarily for the sake of the graph. How do we do this? Because no normal audio hardware supports thinking this way. So when we do our synthesis for these for these products, we compute both the time and amplitude products. So we compute how tall is it and when does it need to happen, and then we use high precision timers to actually deliver that data to the DAC, and we use very fast DACs so that we can output that sample at a very accurate point in time. Our original timing when this was first developed was about 100 millionth of a second. It was our sort of time base. And there's some latencies involved, but we can get pretty close to that as an accuracy for placing points, samples in time. The right is actually a scope capture of one of our oscillators that do this. There's actually 32 steps per waveform at this at that pitch. One of the other interesting things which we're not going to get into is this actually can produce harmonic power, so it's harmonic to the pitch, but above the Nyquist frequency. So like that sawtooth wave on the bottom right, it's very steep. The vertical lines are very vertical. It's going to produce a tremendous amount of a very broad bandwidth signal. And then just as kind of a reference on the left is a band-limited sawtooth as well, which is, as we've seen with these other ones, they're pretty slopey and not steep. So yeah.
I know Nico and I used to work with a lot of software. They used to have like a gigahertz DACs.
Yeah.
And I remember the compute needed to drive the DACs and the ADCs at that sample rate was like insane.
Yeah.
Are you able to get away from using like your normal microcontrollers, or do you have to use like special higher speed?
So the question is, do we need some crazy hardware to make this work? I think is an accurate summary.
Yeah.
And the answer is no. We actually, the original platform we built this on was a processor made by a company called Xmos, which has a bunch of, their whole processor is built around these like real hard time or hard real time guarantees up to 100 millionth of a second, which is where that number came from. We recently had to get stop using the processors because they discontinued the one we used, and we ported it to a kind of more normal processor, and it was some hoops, but it actually works out pretty well. It's not quite as there's some corner cases that end up having to be optimized differently, but yeah, we've been able to like that platform has a 240 megahertz clock that we're using, so as long as you can get somewhere up there, it should be okay. And you can have a DAC that can actually keep up. Yeah, I think that's it for this slide. So, quick summary. Modular synths. You can build the exact synth you want as a user, or the exact synth you can afford. It's a haptic experience. Like, we all spend too much time on our computers these days, so actually being able to get in and touch something and not look at a screen is actually a pretty big driving point for a lot of users. It certainly was for me when I was getting into it. On the production side, the low barrier to entry makes it a market where there's just a tremendous amount of crazy ideas, some good, some bad. Like the variable sample rate thing, like that, just it would be a real hard case to make to develop a whole synth like that, but that's actually been a kind of core technique that we've used in a lot of our oscillators to give it's just some interesting and new tones. And yeah, we definitely use our knowledge from speech, from psychoacoustics, and apply that to making musical effects. Yeah, thank you for listening. Any other questions? What? Oh, yep. There's our contact information. If you would like to talk to us.
Thanks, Steven.
Yeah.
All right, guys. Well, thanks for joining. So because we canceled on Thursday last week, we're going to be doing a makeup tomorrow with Nico covering subtractive synthesis. And then later this week there will be sampling, and then there's going to be FM synthesis. So thanks everyone. And again, if you have missed some of the first few lectures, they're all on YouTube now, so you should be able to catch up. We'll also be emailing out some of the recordings so everyone can watch the ones that we've done so far, because I think it's going to start, especially once we start getting towards the speech stuff, accelerating pretty quickly. So thanks everybody, and we'll see you tomorrow.
Yeah, we're gonna play with this. Shoot.